Greetings everyone and welcome back to the computer screen. In this video, which is part 2 of the distortion measurement, I hope to get the amplifier actually measured. But before I get to that, I want to cover a couple things with the software. In the last video, I did not use the built-in signal generator. That's because when I downloaded this a couple months ago and played around with it, I was actually getting better results using the music player. It wasn't a huge difference, but it was enough that I thought I would get better results with the music player. But I will show you a few things here. I was playing around today and I made some discoveries. So I wanted to run that by you real quick before we get on to the measurement of the amplifier. So earlier today I plugged this loopback cable, which goes from the line out back to the line in, so I can actually use the signal source in the computer and it sends the signal back to the line in where the software analyzes that signal. Now instead of using the loopback, I've plugged my preamplifier in between the line in and line out, and I've already discovered that it doesn't really contribute much to the distortion, so it's okay to do that. So I'll turn the preamp on. So let me turn the signal on. And looking at the manual, they recommend putting the fundamental about 3 dB down, so it's a little more than that. Let me check here. Move the cursor. And we're about 5, so we can stand to turn that up just a little bit. Okay, it's about 3 dB down. But now you can see we're getting what appears to be harmonics. However, using the straight THD measurement, look how low that is, 0.003%. And the THD plus N plus noise is 0.15. Well, as it turns out, these lines are not harmonically related. In fact, if I put my cursor over there, and I'm going to move it, the software is a bit tedious moving the cursor.
Let's see here. We're about on top.
I know I'm on top when this number drops. It's down to 78, 67, 62. Now it's going back up, so I know I go back here. I know I'm on top. 2899 or 2900, that's not a harmonic of 1 kilohertz. And that's what we were starting out with. So something with this software is creating these spikes. They're non-harmonically related to the fundamental. I believe the software only looks at the harmonic node. So if we're at 1 kilohertz here, it's going to look at 2 kilohertz, 3, 4, 5, and so on and so forth. And because there's nothing really there, it gives us a very low figure. Whereas this sees all of this here, and it gives us a higher figure. Okay, so no big deal, right? But watch what happens here when I use another source on the computer. Okay, let me pull up Audacity. I generated a 1 kilohertz signal. Let me start that playing. And we'll go back to this screen. And I have to do the thing with the cursor here. I think I got it set a little too high. We're going to back down. I got to turn it down so it's -3. Right there, minus 3 dB. And look at this. Very clean. There's little spikes here and there, but they're all under 100, minus 100 dB. What's interesting here is that it's still being processed through the computer's Realtek sound chip. It's coming out the same line out, going through the preamp and going back in. So something with its built-in generator puts those spikes in. I'm actually getting better results using Audacity to generate my signal. And another good thing is that this is the preamp's performance, and it's very low distortion. So I can go ahead and use that in testing. It'd be a little easier to adjust its volume control knob instead of monkeying around and getting the computer's levels just right. Well, here's where things go pear-shaped. I generated a 20 kilohertz tone. I set the scale here so we can see all the way up to 97 kilohertz or whatever it is. And I didn't have to adjust anything. It's still about 3 dB down. Didn't have to adjust the preamp or anything, so it tells me the frequency response is very good, at least from 1 kilohertz to 20 kilohertz. And you can see that right there. But look at this. I'm getting the spike here. Oh, there's one thing I need to fix. Whenever you use an external source, you have to match the internal generator frequency with the frequency of the external source you're using, or this will show a high THD percentage. Because it has to match, because that's how it bases its calculations. So I'll pause the video and get that fixed and come right back. Okay, I fixed that. Now you can see the distortion there is much better, but not as low as it was. Let's see, am I on top of that? Yeah. That's the lowest I can get it with the cursor. But I'm getting this large spike, and it may not be harmonically related. So let me get the cursor on top of that. This cursor thing was a little better. It's kind of tedious. 26, 24. So it looks like 24 is the lowest. And that is not quite harmonically related. So I thought earlier it was. But to be only 24 dB down, you know, that's roughly like 21 dB, which would be 10%, but we're showing less than that. So it might be a non-harmonically related signal. I guess what I should try is a different frequency and see what I get. So obviously with a fundamental frequency of 20 kilohertz, the second harmonic is going to be at 40, the third will be at 60, and the fourth at 80, and so forth. So this spike is coming from the computer. So I made a frequency of 19 kilohertz. So the second harmonic would be at 38 kilohertz, and here's our spike again. It's showing now at 25098, about 40 dB down. Actually be like 37, I guess, from the fundamental, but it's not harmonically related. It's something generated in the computer. So since the THD measurement ignores those, I can go by this, though it's really not that low. I could try at 10 kilohertz, see what the distortion looks like there. But yeah, it's kind of a limitation on what I have. But like I said before, this is about all I have to work with here. Okay, so here's what's going on. From the computer's line out, go into the preamp. Again, that allows me to adjust the signal easy using its control, and it appears to have very low distortion, so we don't have to worry about it. Then we move on to the JAT501 amp. By the way, that's the name I've given it. Somebody in the comment section back when I was talking about naming the amplifier mentioned JAT601, but it was designed to be a 50 watt amp, so I'm calling it the 501. So 50 for 50 watts into 8 ohms, 1 being the first amp. So there you go, that's the name. Then of course we need this amp to be handling some current, and we usually make distortion measurements at 8 ohms. So this will be the load, will be a 100 watt 8 ohm load, and I'll use one of these new power resistors I bought. 100 watt power resistor there. Then the attenuator. So what I'm doing, I'm using a 1K ohm and a 100K, or I'm sorry, just a 100 ohm, and that will be a voltage divider. And at the center of that voltage divider, I'll pick off the signal and put it back into the computer line input jack. And again, the reason for doing that is, the output of this amplifier will be very large. It might be like 30 something volts peak to peak, and you don't want to be putting that into the computer's line in port. So you want to attenuate that signal down to something that it could handle. Even though it might have its own built-in protection, at that level you'll just be clipping the signal. So this turns out to be a 11:1 ratio. Why do I say 11:1? I mean, it's a 100 ohm and a 1K. Isn't that a 10:1? Well, let's take a look at this real quick. Here's the resistors, which I'm going to use. Get the meter into the shot. I have the power supply set up for 10 volts. Now let's try this again. Knock the camera over, trying to get the leads in here on it. So if I don't block the meter, exactly 10 volts. So at the center point, we're getting 912 millivolts. So if we actually do the calculation there, move this stuff out of the way. So it's 1K ohms plus 100. So it's actually 1100 ohms. So 10 volts divided by 1100 gives us 0.00090909 amps. So just multiply that by 100 ohms to get back to the voltage at this point. So it calculates out to 909 millivolts. So 10 volts divided by 0.90909 equals 11. Of course, 0.90909 continues on indefinitely, so just ignore that. So you get 11. Okay, so I notated the distortion I was measuring with the preamp at 1 kilohertz, getting about 0.002, and at 20 kilohertz about 0.02 total harmonic distortion. So I'll have that to compare with when I measure the amplifier. I'll test the amplifier at 1 watt and also at its maximum output before clipping. It won't be right at just before clipping because the distortion starts to creep up just before clipping. So it might be just a few watts less. So that's how this is going to work. So without further ado, I will hook everything up and take the first measurement. Okay, it's all set up here. The circuit board's clampulated down to this big heat sink. Here is the 100 watt 8 ohm load. Output leads I tack soldered so I won't have leads coming loose. Power supply, make sure nothing shorts. It might cause something to go bang. We don't want that. And this board here, there's the attenuator. I did make a mistake. The 100 ohm and 1K resistor is a little bit too low a value. Those would overheat when I'm driving the amp hard, so I went up to a 470 and 4.7K. See how that works. This is just a jumper from the preamp into the amplifier's input. Of course, the attenuator goes to this cable into the computer. Like I said, the preamp, the supply capacitors, which from the previous video really improved the output power, so just have those in. Even though I'm using a regulated supply, those really helped things. So, crossing my fingers, hoping this is it, hoping I get good measurements, because I'm getting tired of this thing. I want to move on. I want this thing to be done, so I'm hoping I get good measurements. Okay, onward and ever upwards. Okay, the amplifier is putting out 2.4 volts. That's a little less than a watt, but as close as I can get it. That's critical, because that's probably around normal listening level. And here's what we're getting. 1 kilohertz, 0.005. That looks like my signal. Why did it do that? My signal just quit. But we were getting pretty good. 0.005% total harmonic distortion at low power. So that's good. That means crossover distortion is not really a big issue. Hang on, let me get the signal restarted. So the dominating harmonic is the second harmonic. Then it diminishes. There's a little blip out here. So yeah, that's looking really nice. Okay, it's a couple hours later. I've been really fighting this thing. Over on the scope over there, it's set for about 20 volts, which is 50 watts. And I've been fighting with this thing. And this is not very good at all. 0.07. You know, I move stuff around, and then the signal, then the distortion jumps up to 0.5%, 0.5%. So I've been fighting with this thing. I think I'm getting things back in order. But I made a discovery. This is awful. I didn't want the amp with that much distortion. I mean, we're at 50 watts into 8 ohms right now. It's about as much as my power supply can do. The power rails are maxed out at plus minus 32. Okay, now look at the distortion. 0.007. Order of magnitude better. Matter of fact, if I jiggle these wires around, sometimes, look at that, it just dropped to 0.45. So, my setup is not the greatest, but this amp is even better than this, and this is pretty darn good. You know, it's at near full output, 50 watts. You know, that's the limit of my power supply. I can't turn it up any higher, but we're doing much better. So what was the problem? Well, I was taking the ground off the output, the ground off the input, feeding it into the computer. So what's happening, there's a ground loop, and now that the amp's handling higher current, some voltage drop is introduced along these output leads, and it causes a ground loop and causes distortion in the measurements. So now I disconnected the output ground and brought the input ground lead over. I mean, if you measured it with the meter, it'd still be low, but again, it's just that induced, or not induced, but the voltage drop across the leads here. So now I'm getting much better. It still jumps around. This is not the greatest setup. I bet this amp is probably down around 0.002 if I had a better setup. But all I can say is at 1 kilohertz, extremely happy. I probably should do the 1 watt test again and see if the distortion, well, I can't really go any lower, I guess, with this computer, but happiness. After a bunch of aggravation, now happiness. I was curious of what it would do with a 4 ohm load, and now it's putting on about 80 watts into 4 ohms. I'm getting 0.015. Of course, a solid state amp will always have higher distortion with lower impedance. But again, if I jiggle these wires, look at that. Now it's down to point. Now it's under 0.1. I'm just playing with these wires over here, and it goes back up. And yeah, definitely an issue, but at least I'm happy what I'm seeing with this amp. Okay, well, I'm measuring at 20 hertz now, but I'm not measuring the amplifier. I'm measuring the preamp, and it looks like I'm limited as to what I can get. And it's not the this preamp, because I checked the signal directly, or the computer directly, by doing a loop back, and yeah, I'm getting around 0.02 or so. Okay, I'm measuring the amp again, 8 ohms, and it's a little bit lower now. Maybe if I jigulate my wires a bit, it'll change, but well, the amplifier is not adding anything, so it's safe to say that the amp's doing pretty good there as well. I just need better equipment to see the very low numbers. Okay, now we're at 20 kilohertz, 50 watts, and this is what I'm getting. Probably going to have a hard time with this setup to get very low distortion. I think I can do better than this, but like I say, it's just a limitation of this setup. Of course, 20 kilohertz is going to be the hardest for a solid state amplifier to deliver low distortion numbers, and it's somewhat debatable if they really need that low distortion at such a frequency. But yeah, this best I can do here. Okay, so now we're at 20 kilohertz, and I'm measuring at a little under 1 watt, and this is the reading, 0.03 something. Again, I don't know if I can rely on the setup for high frequency measurement. So you can get all these. You know, this is a spike that's generated in the computer. It's around 24 something. But we're set up to ignore that. So this number will be higher, this number will be lower. Okay, so now I'm looking at intermodulation distortion. I'm using a tone that has a 60 hertz frequency and another tone at 7 kilohertz, and that's at 1/4 amplitude of the 60 hertz. And it's based on some television and motion picture industry standard, something like that. Ignore these numbers because the generator's not set up, so these are meaningless at this point. What I'm looking for is the nodes, or kind of like a sideband of harmonics around this tone. Not necessarily harmonics, I guess, but let me give you an example. If I clip the amplifier, if I turn this up into clipping, this is what you would see. A lot of tones that are multiples of 60 hertz around this. So let me turn that back down. Yeah, so we're out of clipping a few volts, and we're getting little sideband nodes here, but they're around minus 100 dB. So intermodulation is no big deal with this amplifier, at least with this test. I'm going to do another intermodulation test with a 19 and 20 kilohertz signal. However, due to the limitations of this equipment, I don't think I can get a good measurement. Okay, we're looking at the 20 and 19 kilohertz tones. Ignore these numbers. You know, this is not set up to measure right now, so these have no meaning. Ignore some of these bars. Again, from the last video, my computer was throwing some bars up in the 24 and 25 kilohertz range, unrelated to the signal. Mainly I'm looking for a 1 kilohertz tone, which is the difference. If you have a problem with intermodulation distortion, you'll see a sum and difference signal. So I'm looking for a difference signal. 20 kilohertz minus 19 is 1 kilohertz. So I got my cursor there, and there's really nothing down there. You know, it's below minus 100 dB. Another thing I'm looking at is the sidebar tones, and these are below minus 80. But again, I'm working with limited equipment. I can't really measure properly at high frequencies on the computer, but at least I am not seeing a 1 kilohertz tone, which tells me intermodulation issues with the amplifier. Not really a problem. Okay, so that concludes the measurements of this little amplifier board. Very happy with what I'm seeing. Disappointing with the measuring equipment. Now if I had proper equipment, proper cabling, you know, I didn't have this mess. You know, I use BNC connectors and better grounds. When I have this amp on a board, this thing is going to kick ass. It's going to have very low distortion. Much better than I can see here. Yeah, so hopefully I can get some better... well, hi, Snick. Power's off. Kitty going to pass through here. Going to check things out. Had to yell at him. I didn't want him stepping on this earlier when I had the power on. I don't want him shorting things out. And there's 64 volts across the rails. Come on, Snickers. So yeah, I guess I'm going to say this amplifier project is done, set in stone. I'm making another little follow-up video with a final schematic and a couple notes on building it if you want to. And at some point I want to get boards made and distribute those, but you know, for now I'm going to relax a little bit because I got this thing done. I need to sit down and learn some layout software so I can have boards made and to move on to bigger and better things. Well, that wraps it up for this one. Thanks for watching.